I'm Brazilian, and I have graduated in 2007, and I've been working with satellites, with space technology for the last 8 years, and working at Visiona. And today I'm going to talk about the VCUB1 satellite. I'm going to do a mission overview. First, I'll talk about Visiona first to present the company where I work, and then I'll present the VCUB satellite, an overview about the project, the mission, and how is the progress of the mission and the next phases. Here you can see most of the team that work directly on satellite and all the subsystems. And now about Visiona. Well, Visiona is a Brazilian company. It's a joint venture between Embraer and Telebrás. Embraer is a company, multinational company known for building aircrafts, and Telebrás is a state-owned company from Brazil, mainly focused on telecommunications. And Visiona was born mainly to be the prime contractor of the SGDC program. The SGDC is a very big satellite, geostationary satellite aimed at telecommunications. It provides internet for both civil and military purposes. But then Visiona grew, and now it's present in remote sensing market, doing Earth observation services, and also developed the first satellite of the national industry in Brazil, which is the VCUB1. I'm going to talk about a little bit about it now. Well, VCUB is the Brazilian nano satellite for Earth observation and data collection. It's very packed. It's only 6U, but it has a lot of things inside it. It's a dual mission. It has a camera to take pictures of the Earth. It's high quality one with 3.5 meters with TDI, time delay integration technology, and push broom. It has some subsystems developed in-house by Visiona, which is the AOCS system, the OBDH, and the SDR. It's 12 kilos mass. The volume is the 3U volume when it's folded, but then there are solar panels with three layers of deployment. And one of the features of the satellite is that it has very high pointing accuracy, 3-axis stabilized. More about some other characteristics of the VCUB1. It's the satellite has a lot of technologies. Despite of the small size, it has highly sophisticated softwares and architecture, and also lots of the equipment were developed especially for these satellites. It has low jitter and high pointing accuracy, high performance embedded control and communication software developed by Visiona. It has a camera developed by Opto, which is also a Brazilian company. It's a new development, the E3U cam. IMS Kepler did the imaging processing software, and we have also a metal car doing the metal structure, also a Brazilian company. There is a high efficient power generation storage system. The expected life of this subsystem is more than 3 years, so we expect to have lots of pictures of the satellite when it's operating. And also the software-defined radio, which is a technology developed by Visiona to collect data from PCDs that are spread all over the country. PCDs are some platforms that produces data of solar of environmental conditions of the Earth. So we are going to collect this data and then download it to INPE, which is going to be the one that's going to analyze and do some science with it. I'm going to talk about a little bit about the AOCS, which is the subsystem that I worked personally on. It's a very novel system with lots of accuracy, lots of agility. We can point with very low jitter and do maneuvers, pitch, roll, and yaw steering. It has mainly three functions: navigation, which is determination of the satellite states. We use the sensors to measure, and then we give the state of the satellite in terms of attitude and where in the orbit it is now. Then the guidance, we have several guidance modes that we calculate the desired attitude or orientation that we want. If we want to point the panels to the sun, we want to point to a specific target on Earth. And then the control that determine what commands we are going to give to the actuators in order to achieve the desired attitude. Here is a simulation of what we expect of the pictures that we are going to take. It's a comparison between the standard nanosat that is in the market and the VCUB nanosat. We have different spectral bands. We have green, red edge, and near infrared. That these bands benefit the observation of the forest, of the agricultural, and we can do some deforestation monitoring, crops health monitoring. That's the main goal of the observation of the pictures that we are going to take of the satellite. Observe the environment. Oops, sorry. And here is a little bit about the VCUB progress. Like I said, it's a very small satellite, but lots of technology embedded in it. So the project started a long time ago. The mission was conceived in February of 2018, where the satellite was first designed, the mission was first thought, and then we detail it for a year, and then we did a formal preliminary design review in February 2019, 1 year after. And the CDR took a little bit more than 1 year. We had COVID pandemic, and it delayed a little bit our CDR. But then the critical design review was in November 2020. By that time, we were ready to start the AIT, but the equipment, we have some delays with the supplier precisely because of the COVID-19 pandemic. We could only start the AIT once all equipment have arrived, which was only last year, the second quarter of last year. And then we started the assembly and integration tests. And by the time I was invited to do this talk, the launch was going to be in December 2022. So now in March, we would have the first results of the satellite to be presented, but the launch was also delayed. It's going to be only in April, 2 weeks from now, maybe, from the schedule. And so now I can only present what we expect that's going to happen in 2 weeks. So we are going to be launched from California. The launch date is 2nd of April. And the CubeSat is not going to be launched directly from the rocket. What's going to be launched is a satellite carrier that's going to be in orbit for about 10 days. It's carrying lots of other CubeSats, not only VCUB. It's carrying a few satellites, and VCUB is going to be launched only 10 days after the rocket is launched. It's going to be the third satellite to be launched. So here is a simulation of the satellite carrier, putting VCUB in the most precise orbit that we can. The satellite carrier does that, right? It fix a little bit the orbit, has orbit parameters with less dispersion, so we are more certain about which is going to be the orbital parameters of the orbit of the VCUB. And after the launch, the satellite is going to be on. The main subsystems are going to be powered on as soon as it leaves the launch pod. And 30 minutes after the launch, the satellite will deploy the solar panels. And after the LEOP, which is the launch and early orbit phase, we are going to open the UHF antennas, and then we are going to start the mission. The LEOP is not going to be as fast as in this video. It's going to take about 3 to 4 days. So we have lots of tests and things to be done between the solar panels are open and the UHF antennas are open. Just a little bit more. So here are the next phases, what we hope to achieve in the, as soon as the launch separation with this, we put here as T0, 1 week maximum LEOP. We hope to be finished in 3 and 4 days, like I said. And then we are going to start a phase that we call in-orbit test phase. We expect it to end after 3 months from the launch, where we will check all the subsystems, the health of all of them. The camera, we're going to calibrate, do optical adjustment, check the quality of the images, do all kind of adjustments. Then we are going to start a validation phase. This validation is important because the mission of the VCUB is to validate the software that was developed in Visiona, which is the OCS, the onboard software, and the STR. We are going to have 1 month to fully validate these 3 softwares. And after that, we are going to start the operational phase, image acquisition and data collection. At the end of the first year, we put on the calendar another test phase that we are going to do with the same subsystems, AOCS, OBDH, and SDR, but we are going to do more hazardous tests. It's going to test the failures of components, and we put this test to be done after a few months because they are more critical and dangerous. Here is just more details about the launch and early orbit phase. We are going to talk about a little bit of the modes of the satellite, the modes that are going to be engaged as soon as it's launched, as soon as it leaves the launch pod of the satellite carrier. We engage in the minimum configuration mode. This mode is going to be only after the launch separation. Only critical equipment are going to be on. And as soon as the solar panels are open, then we proceed to the next mode. The next mode is the tumbling mode, is the most simple mode of the satellite, is stabilized in 2 axes, is also the most, the safer mode of the satellite. If there is any problems, it will fall back until the detumbling mode. And it's we hope to use it only in LEOP. We don't hope that we have any fallbacks. We also have another safe mode which is called magnetic pointing mode. It's a little bit more um, precise than the tumbling mode. We stabilize in 3 axes, and we have to have orbit knowledge for this mode. And as soon as we stabilize the tumbling mode, we engage the magnetic pointing mode. And as soon as we stabilize magnetic pointing mode, we go to the fast charge mode. This mode is very similar to the previous one. 3 axes stabilized, but we point the solar panels to the sun when outside eclipse, when illuminated by the sun, and we point the spacecraft Nadir when in eclipse. This is to optimize energy generation. That's why it's called fast charge mode. And as soon as we reach this mode, we are going to turn on the cameras, turn on the SDR, and we will deploy the UHF antennas. And then we are going to declare that the LEOP phase is over. And then we are going to start the in-orbit tests, which we are going to do some health tests with the satellite, but we are only going to stay in 2 modes during the whole mission of the VCUB, which is the standby mode. Standby mode is the same as the fast charge mode in terms of pointing. The only difference is that the payloads, both the camera and the SDR, are in standby waiting for the mission to be executed. So as soon as the spacecraft flies over Brazil, it changes the mode to the Earth exploration mode. In this mode, then the payloads are not in standby, it's performing its missions. The camera is in imaging mode, and the SDR performs the data collection mission. This is always autonomous with the changing between modes from standby to Earth exploration mode, but it's always possible to do it by telecommands. And this is the main operation of the VCUB that we hope to be seeing in 1 month from now. Well, that's it. I think I talked about the mission. I now can answer some questions if you have any.
Yes, perfect. Wonderful, Mariana. So thank you again for the overview of the mission. And it was really step to step and really engaging and, clear to follow and easy to understand for individuals as well. How the mission is going to be executed. The timing is also just perfect. As you mentioned, there are a couple of weeks from now the launch is going to be happening. So we're going to be crossing our fingers for a successful launch and a successful deployment of the VCUB1 as well. So there are a couple of questions in the chat, and then I have plenty more from my side as well. And we still got like 8 minutes, so I think we will be in time to cover all of those. Then the first question is from Antonio Macado. And his question is that, first of all, he's glad that he met you here. And then the question is there any big difference between the VCUB1 and those of big satellites, such as Sentinel-2, and on the other hand, those of the small sats like Planet, for example? That's
Yes, I think the main differences are the spectral bands of the camera. The camera is very, very new technology. It's really small, really packed. Lots of big mirrors that are used inside the camera. So the quality of the images that we expect to achieve are very high, much higher than the ones that are in the market. And also the AOCS, the hardware that we chose has very low jitter, and the software is very sophisticated. We hope to achieve really, really low levels of very high stability and very low errors, both pointing errors and knowledge errors. So that's going to increase the quality of the images, and it's going to be much higher than the ones that we have now in the market that we hope to see in a few weeks.
Perfect. And Antonio is commenting again that it appears that I misread the question just a bit. So he's asking the difference in terms of the AOCS.
Okay. In terms of the AOCS, we have 2 star trackers that then I think most of the satellites use only one. So we combine the data from those 2 star trackers to have a sensor fusion algorithms, and we also that increases the pointing accuracy and the navigation, the determination of the attitude precision. And also we have novel ways. It's a very modular system. So we have lots of guidance modes. We can do some with really easy commands. We can command to point to a specific target. We can command to do a push broom image. We can command to do even backward imaging backwards, put your steering at 90 degrees. It's very modular approach, and it's very but we use the same equipment that they are in the market. We use reaction wheels, magnetometers, and star trackers, gyros, sun sensors, and magnetometers, and we combine all of the sensors and use the actuators to produce high precise pointing system.
Perfect, thank you. And there's another follow-up question, Mariana, from Antonio. He's asking, what is Visiona's plan to build a VCUB constellation?
Well, it would be nice if this plan turns into a reality. Now that we are going to launch VCUB, I think it's going to be much more in visibility of what it can be done, and I think it's going to be a good marketing of what we can do with one satellite. So one satellite is not enough for a country as big as Brazil. So we hope to launch more of it, to cover with more with the lower revisit times. And we have lots of potential clients that are going to be interested in have images with the lower time frame between them. So yes, we hope to launch more and more VCUBs in the next years.
Perfect, and it's wonderful to see again how the Brazilian space industry is already almost booming, right? A lot of new players and launch players as well are emerging again in that region. And there's another question from Sergio, our previous speaker, and he's asking, can you speak a little bit about the expected outcomes for VCUB? You mentioned spectral band coverage for your optical systems, and I'm curious about what drove those requirements. Are you primarily providing the data to commercial groups, data brokers, or the Brazilian government?
Yeah, the idea is to work with the clients that Visiona has already, which are mainly focused on environmental monitoring, and we have lots of agricultural I forgot the word.
Applications, bro.
Yes, agricultural applications, and also to monitor the level of reservoirs. And in Brazil is a very agricultural country, so
Mhm.
the government is the one most interested in using the VCube images to do some detection changes, deforestation monitoring. That's what we do most with the constellation of satellites that we work with. And we chose those bands because they are more adequate to do this kind of monitoring. It's going to be easier to detect uh, crop health, crop growth, and also deforestation, where in area the the um, the forest has been cut. That's the main goal. That's why we chose to use these bands, because of the needs of the market that we already have, to fill the gap, the hole of the market, and to provide some more um, some a better way to do what we already do, to with more quality.